No questions? Should just proceed. Okay. Let me do this here for quick. I'm going to say this is going to be the analysis for the concrete section, the reinforced concrete section. And the purpose of this analysis is to find out the moment capacity or the strength of the section. It is not to study the performance of the section, like in the cracking moment thing. The cracking moment was only to study the performance of the concrete at the early stage of loading. And at the cracking point, we assume that the steel is not working. This is also one of the assumptions. So in here, the concrete has already been cracked, and the steel is triggered. The force now is becoming as a tension in the steel, and we assume that the steel has been yielded already. When the steel is yielding, it means that you're going to be here at a very high strain, right? And in that case, you're going to say the tension the steel is going to be equal to AS, total cross-section area of the steel, multiplied by the yield strength. Now, usually, your neutral axis is going to be, let's say, about in this location, roughly. To complete your analysis, you need to apply the equilibrium condition on this cross-section. So when you cut the section here, the tension is going to be the same as the compression, because you don't have any external applied forces. If I have a compression axial force, let's say that this is a column, right? I'm just moving here to a different example. If I have a column, I would have here a point load is going to be like P, external force. Now, the external force in this case is going to be equal to the difference between the tension and compression. You need to consider it. But in our case here, I don't have external applied force because it's just a beam. There is no axial load in this beam. This is going to be my assumption, right? In some cases, beams would have a little bit of compression, axial compression, external. But in this case, we assume that there is no axial compression force on the concrete beam, just moment. And the moment is going to be resolved into a tension and compression components. Now, for equilibrium, again, C is going to be equal to T, meaning that AS times Fy equals this ordinate of the stress, 85% of F prime C, times the depth A, times the width B, which means the volume of this compression block. Once you set them equal to each other, now you start to think what is given, what's going to be the unknown. AS is going to be given to you, or maybe you can assume it. Let's say in real practice, you're going to be throwing some bars there and you say, okay, here's AS. Yield strength, yeah, you have yield strength. This is going to be the material property. Concrete strength, also material property. B, the width of the beam. You need to start with a section. And A is going to be your only unknown. So by setting C equals to T, you can solve for this A. Once you have A, you can figure out the depth C, depth of neutral axis, with this beta factor, beta 1, that we have a graph for. Now, once you have also C, you can figure out the strain in the steel from these two similar triangles. You can say, for example, 0.03 divided by C, right? For this triangle, the top one is going to be equal to the strain in the steel divided by D minus C. So the distance from here to there is going to be D minus C. And with that, you figure out the strain in the steel. Now you have the strain in the steel. Back to Matt's question about what would you do next? You can do C over D to figure out the phi factor, or you can just take the strain in the steel and find out the phi factor value. Now the moment, internal moment, is going to be equal to C or T multiplied by the distance. You can call it Z if you want to. Some people call it YCT. And how much is the distance from here to there? You're going to say it's going to be equal to D, the depth D, minus A over 2 for the distance from the tension to the compression. Now we discussed the amount of reinforcement that you put there in the steel. When I put lots of reinforcement, let's say instead of putting, let's say 3 number 8, I decide to put 10 number 8, just lots of rebars than normal. Now the tension force here is going to be higher. When you look at this number, right, you take AS multiplied by Fy, this number is going to be growing up. When this goes up, it means the depth A also is going to be going up.
Can you repeat that again?
Okay. When you add lots of reinforcing, what's going to happen? This tension force is going to increase. Correct?
Yes.
And then you need to set T equal to C. F prime C is not changing. This is a material property. It comes with the concrete. When you purchase the concrete, let's say that you order 4,000 psi concrete, it's going to be constant. The width B is also constant. You cannot change the width of the beam when you're adding more reinforcing. So when you're doing this, you set one parameter to be your variable, and everything else is going to be constant. So for example, if I said if I add more reinforcing, it means the depth D is going to be the same, and the width B is going to be the same. Yield strength is going to be the same. Concrete strength also is going to be the same. I'm not changing those. I'm just changing the amount of reinforcing. So what I'm saying, the tension force here is going to be going up. So okay, this goes up like this. So what else? I'm going to say T equals C. B is the same. F prime C is the same. 0.85 is the same. So the only variable is going to be going up is A. So what happens to the depth of the neutral axis? C and A, they're going to be going up. What does it mean by going up? It means that I'm going to be going to case number 2. You see this case number 2? This is going to be a result. This is going to be the neutral axis location, a result of adding loss of reinforcing. When you add loss of reinforcing, neutral axis depth is going to be coming down. So what's going to happen to the steel strain? Look at this blue line. Remember this blue line from last time? What's going to happen to the strain in the steel? Is it growing up or coming down? Any answer on this? When the neutral axis goes down from this red line to case number 2, what happened to the strain in the steel? Strain in the steel is going to be going down. So this epsilon S is going to be going down in this case. So when epsilon S goes down, it means the phi factor is going to get reduced. Let me take you here to this slide. Look at this. Here's the strain. When the strain goes down, when it is like here, what happened to the phi factor? Phi factor here used to be 0.9, now drop down to something, to some value. If you remember this discussion, right? Which means adding lots of reinforcing will reduce the phi factor for you, which is not very desirable. You don't want to do this. So if you have a beam and you don't have enough reinforcing, in some cases the solution is just to add some reinforcing, right? Then you can just achieve the strength you wanted. In some other cases, you add reinforcing and it is not working out because you're kind of chasing your tail. Now, you add more reinforcing, so the tension force is going to be going up. At the same time, the phi factor is coming down. This should be like an optimum design. With this given cross-section area, there is the best reinforcing that you put in there with it. It's not just adding reinforcing, adding reinforcing. You see my point? When you go here to the left, when the strain in the steel becoming low, you should expect compression control failure, which means brittle failure, unexpected, not good. That's why the phi factor is lower. Someone's gonna say, why do I need to look at any failure at all? I mean, I'm not designing this beam to fail. You can say yes, but when you have excessive load beyond the design loads. So let's say that you start to add some loads because no one was listening to you. You designed for certain given load, but they added more equipment, weight, and things like this, right? So instead of seeing here brittle failure because you're going to be compression controlled, you'd like to see here ductile failure. In a ductile failure, you're going to see more deflection of the beam. So it's going to give you a chance here to escape if you want to. You can just get out of the building. But if no deflection, no cracks, you're going to be looking at the beam and say the beam looks good. We should stay here. And then all of a sudden, you're going to have this brittle collapse to the beam that you don't want to see. Now, the moment strength that we talked about, if I may take you back here, as I said, the moment is going to be equal to tension or compression multiplied by the depth or the distance between the two. Some people again call it YCT, some people call it Z, which is D minus over 2. Now, this moment here, I'm going to call it internal moment. It's not external moment. External moment is going to be that moment when you do beam analysis. So if I have a beam, I do the analysis of the beam, I'm going to call this external moment because of the external applied loads. This is here is going to be internal moment within the beam section itself. So this external moment eventually is going to be equal to the internal moment. Okay. Here are the same equations that we discussed. Here is the tension force, compression force, set them equal to each other, solve for A. So as I was saying, when AS goes up, what happened to A? A also is going to be going up, right? Because everything else is going to be the same. But the problem is the phi factor is going to be going down. Because at this case, when A goes up, I'm going to take you back here. When A is grown up in value, neutral axis is going to be going down like here. And look at the strain distribution. The steel strain, instead of being here, is going to be coming down, and the phi factor reduces. But if you put less reinforcing, what's going to happen to A? Look at the equation. Now, A, we're going to be reducing AS, which means less reinforcing. A is going to be also going down. We're going to be going to case A. It's going to be more of tension controlled side, right? What happened? Neutral axis is going to be going up because A is reducing. Now look at the strain in the steel. It becomes too high. So the phi factor goes up. I'm not saying that this is like a bad option or a bad solution, because in some cases you are limited with the depth. And there is no way out of it. You need to go with the shallow beam because depth restriction, overhead restriction. So in a case like this, you may have to go with this case too, but it is not preferred. If you ask, if you have the chance to make the beam deeper and you put more concrete and this amount of reinforcing, you do it. If you are limited in depth, in this case, you start to add more reinforcing, but you need to understand you're going to be pushing your phi factor down and you may go to a case like case 2. So this needs to be clear to you guys so that you have the feeling when you start to add some reinforcement to a beam.
So like for the phi factor, is it best to have it in the transition area instead of it being on either extreme of the tension control? Or
The best is to have it here.
Oh, okay.
The best is to keep it here, if possible. But if you have to reduce it a little bit, here is gonna be okay. If you have to go here, I mean have to, which means there's no way out. You cannot add concrete because you have this limitation of the depth and the width. Because other stuff happening around you. It could be mechanical ducts, it could be dark pressure and available overhead, you know, the height, you don't have lots of clearance. So in this case, you have to stay with a shallow beam, and in this case, you just add more reinforcing, and you should expect your phi factors to be low.
Okay, thank you.
Having low phi factor, it means that you're not using the material efficiently. To be efficient, you'd like to use higher phi factor. Look at this equation here. Equation says moment equals tension force. So it is true. You add here more reinforcement, right? You add more material, more cost. And then when you add lots of material, you're not really using it efficiently because the phi factor is going to drop down, and the phi factor is going to be multiplied by the total moment. So you're not gaining, I'm going to say, you're not gaining that benefit when you're adding lots of reinforcing. This is what I'm trying to say. But you need to be aware of it. Now let's go through one example. This should be very good example. It shows you all the details of the analysis. It says here concrete strength is 4,000, yield strength is 6,000, and you know that this code is PSI, so everything here is going to be in pounds and inches. It says for simplicity, neglect the hanger bars. Where are these hanger bars? I'm going to say these 2 bars on the top. Just ignore them because they're not going to be in tension. So we decided here just ignore them. We have here ties, number 4 at 14, not contributing here to the flexural strength or the moment strength, but we have them for other reasons. It says here, determine the nominal moment strength Mn at the design moment strength. Moment strength, which means the capacity. So let me write this down. This moment strength means capacity. How about the cracking moment? Is the cracking moment a capacity? Just wondering from you guys. I'd like to hear it from you.
Yes.
We discussed this previously. I'm gonna put it here, and please remember this. Cracking moment is a limit state. And what does it mean by that? It's just measure of the performance of the concrete section. All right. About this moment that I'm talking about, Feynman, is this a capacity? Let's say yes. Feynman is a capacity point. Okay. Let me repeat this again. Is the cracking moment a capacity? Can I use it in my design?
No.
No,
No.
you don't
No.
use it in design. So if at any case I ask you for the moment capacity and you answer with the cracking moment, means that you answer something different that I didn't really ask for. This is what's called here moment strength or moment capacity in design. This point here, it just explained to you how the concrete section works. That's it. Okay. Now we need to figure out this Feynman. So let's see how it's gonna work. Let me also point to something here. Total concrete depth, as you see here, 16 inch. Width is gonna be 10 inches, B. The clear cover, you see this cover, sometimes we call it also clear cover, is 1.5 inch. What is this 1.5 inch? From where to where? You can say from here to here.
Do we consider that in our analysis? I don't think so, right? Because it's not the behavior of the concrete.
Yeah, I'll tell you exactly what is needed out of this exercise. I'm looking for this depth D, right? So you see here the depth D defined for you? You see it? Depth D. What is D? D is going to be the distance from the centroid of the bars, right? Which means the tension, all the way to the top compression. Just wondering, do you have this number given to you? You see, no, I don't have it. I have the total depth H. I have the clear cover, and then I have the bar size and all of that. But this is what I'm looking for. You see this? D to the center of the rebars. So based on this H and the cover and the tie size and the rebar size, I'm going to be determining the depth D. This is the reason that I have the entire section, right? Information. So I'm going to say, how about this D depth here? How can I figure this out? I'm going to say, well, it's not really hard, because to find out D, you need to take 16 inch, subtract 1.5 inch for the cover. Now you have it up to here, correct? And then number 4 ties means 1/2 inch rebar, which means the distance here for this rebar running across sideways here is going to be 1/2 inch. Correct? Number 4 means 4/8 of an inch is going to be 1/2 inch. How about this rebar size? What is number 8? Can someone remind me here what is number 8? The size of number 8?
1 inch.
1 inch. So how much is 1/2 of it? Like the radius? It's going to be 1/2 inch. Meaning from this red line to this red line is how much? You have 1/2 inch for the tie, 1/2 inch for the radius. Total distance from here to there is 1 inch. All right, now take 16, subtract 1.5, then subtract additional 1 inch. So take 16 minus 2.5 inches.
14
right?
and a half.
Maybe 13.5. All right, here it is. 16 minus 2.5. Again, where's the 2.5 coming from? 1.5 inch for the cover and 1 inch from the bottom of the cover or the bottom of the tie to the center of this tension rebar. So I'm going to say 16 minus 2.5 is going to be 13.5 inch. This is going to be this equation here. You're good? Any questions? Yes? No?
Good so far.
Okay, good. How about the cross-section area? It says here 3 number 8. Right? You gotta go here to this table. What does it mean by number 8? Number 8 means 1 inch diameter and the cross-section area is 0.79. You cannot try to figure out this AB by doing any calculations. You don't do it this way. This is wrong. You just need to look it up from here. So for this AB, number 8, I have a cross-section area of 0.79. Now let me go here. 3 rebars times 0.79 is going to be 2.37 square inches. Now this is AS. So what is this AS? What is 0.79? Do we know, what do we call it? Like a symbol is used for it? I'm going to say AB, A sub B, right? Then we have it here. If you remember, this is going to be AB, right? A sub B for 1 rebar. Right, first assumption. I'm going to assume here that the steel is yielding already, correct? So what does it mean? It means the stress in the steel is going to be equal to F sub Y. Taking this old equation, if you remember this equation that we used last time and also we discussed this time, you said the tension equals to the compression. With that, you solve for A, compression block depth. You say, okay, AS times Fy, 0.85 F prime CB. Here's AS times Fy. The tension force is going to be this one here. See, this going to be the tension force. You say, here's the tension force, 142. How do you do this? You take Fy of, how much was Fy? 60,000 psi. How much is this in kips or ksi? Is equal to 60 ksi. If someone try here to help us and just take 60 multiplied by 2.37, would you get 142.2? Who can help with this?
Yeah, you'll get the same thing.
Okay, good. How about F prime C? What did I use for F prime C? I used 4 ksi. Yeah, it's 4,000. If you go back here, 4,000, which means 4 ksi. Now, units, I need to be consistent here with units, right? So if I used here ksi, I need to use here ksi. So be careful because some people would just use here 60. When it comes to this one, they put 4,000, and with that, you get very small number for the A. So be careful about units. I'm getting here 4.18 for the compression block depth. Where is this here on the drawing? I'm going to say on the sketch, let's give you right this one. Here it is, compression block depth. Now I need to get to C. How can I do C if I have A? I guess I have a factor of beta 1. And because beta 1 is going to be less than 1, you take A divided by beta 1, you get to C. Let me see how this is going to get done. Here it is. Beta 1 is 0.85. Where is this? I mean, do you see it before? You can say, yeah, let me take you back here to this one. When the concrete strength is 4,000, your beta 1 is 0.85. If you go a little bit higher in concrete strength, the beta 1 factor is going to drop down according to this line. If you go to 8,000 and higher, it's going to be 0.65. Now, okay, I said fine. I understand that. Let me figure out here the C. That is going to be equal to A, the 4.18, right? Which is the same as this, divided by the beta 1 factor, the 0.85. Therefore, C is going to be here 492. So, okay, good. Let's give it depth of neutral axis. Now I need to check the strain that I assumed. I assumed that strain in the steel is more than 0.02, which is the yield strain. So first, how much is the yield strain? We did this a few lectures ago, but here it is. You have it here written. This is going to be the yield strength, 60. It's okay now to do it in KSI. Divide by 29,000 to modulus elasticity for the steel. You get 0.0021. What units should I use here for the strain? Can someone help? What units?
Isn't it unitless?
No units. Yeah. Exactly. It is unitless. No units here. It's inch by inch or feet by feet, so it's going to be unitless. Now, let me figure out here the strain in the steel at the bottom. So look at this equation here. If you take here D minus C, where is this D minus C? Can someone help me with this? This is D minus C. trying to figure out where is this dimension in here. And say, where is D? D is from here to there. Subtract C. Therefore, I'm talking about this distance from here to there, right? This is going to be this distance here. So now I understand where this is coming from. D minus C is going to be this distance. If I may see here, let me take 0.03 divided by C, correct? For this triangle. Look at this triangle here. Take 0.03 divided by C is going to be equal to the strain in the steel divided by D minus C. Here we go. 0.03 divided by C for the first triangle, the top one, is going to be equal to the strain in the steel divided by D minus C. Your only unknown here is going to be the strain in the steel. You can run the numbers. You're going to get here 0.005. This is good. High strain in the steel. This is great because it's going to be more than the yield strain. So my assumption turned to be correct. In some cases, you backcheck the strain and you're going to find it to be lower than this strain. In this case, your assumption that the steel stress is going to be at Fy is wrong, and you need to repeat your work differently. So, okay, now I was able to prove here that the strain in the steel is higher than the yield strain. Now I need to take this value back and also check the phi factor. You say here is a 0.005. Should I be in this side or be in this side? Is this shown here correctly, or I should have stayed here? Because the strain in the steel, according to this, is going to be 0.0052. Is 552, is 5.2 in this side or this side?
On the right.
On the right side, because you see the increased direction is going to be according to this arrow. So I'm correct. The phi factor is 0.9. This is great. Also, I confirm my assumption. This is very nice. Good. So what do you do next? Next, I need to find out Mn, nominal strength. This is what I've been asked in this exercise. Mn is going to be equal to the tension force, the 142, multiplied by 13.5. What 13.5? Say the depth, D. Subtracting A, which is 4.18, divided by 2. Where is this A? Here is A. 4.18, you divide this by 2, which is 2.09. So this Z distance is going to be from here to there. It's going to be the depth 13.5, subtracting A over 2. Okay, I use this here. Now my answer is going to be in what? This here is going to be in kips, right? Units. I need to think here about units. It's going to be in kips. And this term here is going to be 13.5 minus 2.09 is going to be in inches. Therefore, the moment, resultant moment here is going to be in kip inch. You need to keep track with your units. Usually, if you like to report a moment, you report it in kip foot in concrete design. If you do design, it's going to be in pound inch or pound foot. But in concrete design and steel design, it needs to be in kip foot. So be sure when you're solving for any moment that you do it in kip foot. And please remember this. Okay? Now at the end, this 135.2 kip foot is going to be the nominal. I need to reduce it by the phi factor, the 0.9, and I end up with the 121.7 kip foot. Now which one is the strength? The moment, the design moment strength. Is it going to be this value, the 135 or the 121 for you? 121.7. This is what you call here the design strength. How about this one? What do you call this? Called nominal moment design strength or nominal moment strength. You don't really call design strength. This is going to be the design strength, which is female. Are we good? Any questions on this example, or should I assume that's clear? Everybody's good with it, and we just move forward.
I have a question. Sorry.
Go for it.
I have a question regarding how you were able to get the effective depth. Why is it that you subtract 2.5 instead of 1.5?
Okay, I'll get to that. I have a question here. The design is also capacity. If I just say design moment, let me put this in perspective. Design moment. This means demand. What does it mean by demand? Like 1.2 dead plus 1.6 live. We call this the demand. If I say design moment strength, is gonna be this one here, theme man. If I say moment strength, is gonna be this value here. So this one here, I have more than one name for it. And so, okay, here are the names for this. This one I can call it design moment strength. Also, I can call it, let me make this larger. So this can be the first name for it, if you like. It can be also design strength. Moment strength. I also can call it flexural strength. Okay. If you just say design moment, it means the demand. M sub U, which is in here, it's gonna be M sub U. Now back to your question. How did I come up with 13.5? Why did I subtract 2.5 inches? It's gonna be taken in here. The D distance is a distance from the top compression to the center of the rebar, correct? Are you there? All right.
Yes.
Good. This 1.5 inch, it is not really to the center of the rebar, isn't it? Is it to the center of the rebar? 1.5 inch?
No.
1.5 inch is the bottom of this rebar, but I want it to the center of the rebar. So what I said, from here to here is gonna be 1.5, and from here to here is gonna be an inch. How did they come up with it? You have number 4 ties, and what does it mean by number 4? Just in case if you forget, number 4 means 1/2 inch in diameter. Look at this, and number 8, 1 inch. So from here to there is gonna be 1/2 inch, and from here to here is gonna be another 1/2 inch because this rebar is an inch. So when you add this 1 inch to 1.5, is gonna be 2.5 when you subtract it out of the 16 to get to the D distance. Did they answer your question?
Yes, thank you.
No problem. So okay, now we're good with this example. Now let's try here, just for sake of discussion. What happened if I put the number 8? So this is exactly the same problem. Look at this. Same section properties. 10 inch, 16 inch, 1.5 inch cover. I have 3 number 8. Now all of a sudden I throw lots of rebars because the capacity was not enough. I'd like to see what is the effect of doing this. Any expectation from you guys? What's gonna happen to the V factor?
It's
gonna-
reduce.
It's gonna reduce, right? It's gonna go down. Now let's exercise this. Good. And look at the concrete. Becomes here 5,000. I added more concrete strength. Here's the depth. It's gonna be the same. AS. Look what happened here to AS. It used to be 3 number 8. Now it becomes 10 number 8. I'm gonna also start with this assumption. I'm gonna say, you know what? Let's assume that the steel strain is higher than the yield strain, which is a limit. Let me also try to do this A, depth of neutral axis. Look what happened when you do AS equals. Here's the tension force, right? What happened to A value? 11.15, 11 inches. It does make sense. Does this make sense to you guys? When you look at this 16 inch and then you see neutral axis gonna be almost here. Does this make sense to anyone? It doesn't make any sense, right? This is a lot. This is going very deep because I have here lots of reinforcing, which means something is wrong here in the analysis, but we can figure this out and then discuss it. You can see the C is gonna be 13.94. It is even more than the depth D. Look at this, the C factor, because the concrete strength is 5,000, your beta factor is 0.8. Look what happened to the C depth. This is crazy because this depth here is 13.5. So when you have 13.5 and your C is gonna be more than that, it means that there is new neutral axis, correct? Something is wrong. Neutral axis is lower than C. It doesn't work this way. And look at this C, 13.94, and the total depth is what? 13.5. It's even more than the depth. So this assumption is incorrect. The whole thing here happened because when I used 60 for this f sub y, I used 60 KSI. That was completely wrong. That was just too much. Because that was, I mean, what was the result of using 6 KSI? The depth becomes very big, the depth A of the compression block, and depth of neutral axis also becomes huge. It doesn't work this way. It means my assumption here is wrong. The steel will never get close to the yield strength. It's okay, this makes sense. Now, since my assumption is wrong, it means the steel was not yielding, and the steel stress is going to be somewhere between the 0 to the 60. But I don't know exactly how much the steel stress is going to be, unless I know the steel strain. Now, in the previous example here, I just have usually one assumption, and then I just solve for the whole thing, which means I assume here that I'm going to have only one unknown. By assuming that the steel is yielding, I have only one unknown. I can just solve for it all the way to the end, which is the depth A and then C, and then after that the moment as a result of my analysis. Now in this case, I'm gonna have two unknowns. One of these two unknowns is gonna be the steel strain, and the other one is gonna be the depth C. I don't have both of these two. So again, in the past, I just assumed this T to be at 6 KSI. Now I cannot go with this assumption. It's okay. Let me write here the equation for the compression block depth. Here we go. A is equal to AS, FS. It is not now FY anymore, right? Because the steel is not yielding. So let me write this down. Steel is not yielding. So what does it mean? It's going to be now FS. It used to be FY. Let me take you back here a couple of slides. Okay, here we go. It used to be 6 KSI. Now it cannot. It's going to be just FS. And my understanding is A is going to be equal to C times beta 1. Yeah, I know this. And the steel stress is going to be equal to the modulus elasticity, the 29,000 KSI, divided by the steel strain. I know that. I can take all of those three equations and put them in one equation if I want to. So, okay, good. A, replace it with C times beta 1. Here we go. It's right here. The steel stress, I'm going to replace it with epsilon S times the modulus. This symbol here should have been what? Anyone can help me? S, not Y. This is a typo. All right, guys? Can you please take a note of this? It's not just F sub Y. F sub Y is going to be a special case. It's going to be equal to epsilon S times, which is this one, times ES, only at the yield point. But generally speaking, this Fs is going to be at any point through the linear relationship, the elastic range. So if I'm going to do this, the strain is going to be in the X direction, the stress is going to be in the Y direction, and between the yield point and between the 0 point, this is where I'm going to have this equation valid, right? So I'm talking about this range here, the elastic range, right? This equation is good for it. Fy is going to be the highest stress, but at any point it's going to be called F sub S. So okay, let me take F sub S here out and replace it with ES times the strain in the steel, epsilon S, which is this one here. Okay, this one is what is going to be coming from here. So great. Now I have new equations. What are the unknowns in this equation? I'm going to say B is constant. I mean, it's not going to change. F prime C is the same. ES is the same. The strain in the steel is going to be one unknown. AS is given. Beta 1, I have it from the strength of the concrete is going to be 0.8. So I'm going to have here two unknowns. Can someone help me? What are these two unknowns in this equation? What are the two unknowns in this equation? Help, please.
C and the strain of steel.
Very good, thank you. This is correct. So I don't have this. Do I have another equation that relates C and also the strain in the steel? You can say, yeah. You have an equation that you used, which was based on these two similar triangles. If you remember these two similar triangles, I'm gonna take you back here. This equation is also, I mean, based on this, I can drive an equation. And here's the equation. Look at this equation here. Based on this symmetry, I can say 0.03 divided by C is going to be equal to the strain in the steel divided by D minus C. Now, in this equation here, how many unknowns you have? Look at this. I have C, C, and I have epsilon S. D is given, right? You have it. You solve for it. It's going to be 13 and a half. It's going to be the same two variables that I'm looking for to solve it, right? It's going to be the C and the strain in the steel. So I'm going to move forward here to our example. I'm going to say, look at this equation. It's going to be the second equation, right? So this is going to be the first equation between epsilon S and C. It's going to be the second equation, again, between C, repeated twice, right? And between the strain and the strain. Now I have two equations, two unknowns. I should be able to solve them. But let's do it here numerically. So I said here, let me take this equation. It's going to be C equals. I'm going to take this beta 1 in the denominator. So it's going to be equal to 7.9 AS times ES times the strain in the steel is still my unknown. So I'm going to put a box around it. Divided by 0.85 F prime C, B, and beta 1. Here's beta 1. Here is B. Here is F prime C. This is going to be the 0.85. I still have these two unknowns. I'm going to clean this equation a little bit. Finish it. I'm going to be ending up with C and epsilon S. And here's the multiplier. Now I guess you appreciate when you put less reinforcement, right? And else is much simpler. So adding lots of reinforcement is not helping you as an engineer because you're going to be doing more analysis. Now I guess I should be able to solve equation 1 and equation 2. Solve them together. You get C and A. Right, here we go. Now I solve for C and A. Once you have C, can you figure out the strain in the steel? You can see, yeah, let me go to which equation? If you have C and the strain, go to any one of these two equations. The strain in the steel equals C divided by this number, right? You can do it this way. Here's the strain in the steel. Take this C, divide by this number, this big number. You get the strain here in the steel. How much was the strain in the steel at the yield point? Anyone recall this number? At the yield point. How much was it equal to? Yes? Yes, exactly. 0.02. Thank you, Jorge. This is correct. So this is like half of it. I'm expecting now that the stress in the steel to be also half of 60 because you can just follow this equation here, right? Here's Fs. I said it's about maybe 30, turned to be maybe 32. Not bad. All right. Based on what equation? Based on this equation. The stress in the steel is going to be equal to this strain, just multiply this by 29,000 and tell me what would you get. It's going to be 31.9. So when you assume that the steel stress is 60 KSI, like in the previous slide, that was just too much, right? Because the actual strain, the stress in the steel is about 32 KSI. Also, let's try here to look for this phi factor. When you do C over D, how much is C over D? 686. So what does it mean by 686 in terms of phi factor? Look at what happened here. C over D is going to be 6, a little bit above 0.6. It's going to be in this side. Your phi factor would become how much? 0.65. You're given the compression control. It's not really desirable, but this is what you get. Right? Now let's complete the equation and solve it. M sub n is going to be equal to AS multiplied by Fs. Look at the previous couple of slides back. AS times FY, how much was it? 474. Now look what happened. It dropped down to 252. Wow. Why? Because this is now equals to 7.9, which is AS times this 32 KSI. So, okay, here's the tension force. 13.5 minus A over 2. Where did you get this 7.41? I'm going to take you back here one slide. Say, here's A, 7.41 from my analysis, divided by 2. I have it here in kip inch because this force is giving kips, and this dimension here is giving inches. Take this divided by 12, it's going to be like in kip foot. Now reduce it by the phi factor. Look at what happened. Reduce it by phi factor. Now you have 133 kip foot. I said, okay, this is fine. This is what I have. Any questions? Now I'd like to do comparison between the two solutions. I'm going to take you back here to the previous solution. Look at the moment strength, the flexural capacity. 121.7 kfoot with how many rebars? Anyone remembers how many rebars? 3 rebars. Now you added here 7 more rebars. How much increase in the strength did you gain? A lot? Did you gain lots of strength? No, you just moved it from 120 something, like 122, let's say, to 134. Not that much. And you added lots of rebars. It's not really helping because the phi factor just dropped down when you add lots of rebars. So you didn't really help yourself out. So in a case like this, maybe an efficient design is to increase the depth of the beam. Because when you increase the depth of the beam, you're going to be adding lots of strength without changing the A. A is not really based on D. Let me take you back here to one of those equations. Look at this analysis here. It says A equals ASFY 0.85 F prime C, and here's B. It is not really based on the depth. It just based on the amount of steel that you put there and the material properties and the section width. And this is how you reduce the depth A. Adding tons of reinforcing is not really helping because it's going to be reducing your phi factor to 0.65, and therefore you dump maybe 3 times the amount of reinforcing that you started with, but you just gain maybe 10% increase in the strength. Not good, right? So use the answer is not to throw lots of reinforcing bars because this may not help you that much. This is like an optimum design. You need to balance between the amount of concrete that you have there and between the amount of reinforcing bars that you put in there. Not just to dump the reinforcing and say, now let's get care of it. You cannot say, for example, for 3 rebars, the strength is 120. When I put 9 rebars, the strength, now without knowing all of these facts, you're going to say the strength is going to be maybe 360. Why? Because I added or I tripled the amount of rebars. And I'm expecting the strength to be tripled, but it didn't happen this way. You just gained 10% additional strength. Any questions?
Excuse
No?
me, Professor.
You're good? Yeah, go ahead.
Why we couldn't use F sub y in A equation? And
Which
the
one?
tensile still hasn't yielded.
In here?
No, in
In the
page
previous?
19. Yeah.
Okay,
Page,
I'm going to go back.
it's
19?
Page 19.
Yes, I did it. I used Fy of 60.
Why the tensile still hasn't yielded?
It didn't yield because when you look at the strain distribution here, right? If the neutral axis depth here is right in the middle, just imagine that you have this beam depth, right? And the neutral axis is going to be right at the mid height. The strain here is going to be 0.03, and the strain here is going to be how much? 0.03, correct? If this neutral axis is going to be in the mid height, when the strain here is 0.03, the strain here also is going to be 0.03 because the strain here is not changing. is going to stay as 0.03. You know that, correct?
Yes.
So if the neutral axis is right here at the mid height, this is about the mid height of the beam. Let's say if the neutral axis is about here, the strain on the top is going to be the same as the strain on the bottom, is going to be equal to 0.03. When you assume that the stress in the steel is 6 psi, you end up with a case like this. Neutral axis is going to be like here, or even deeper. It's going to be almost here. Right? It's about here. What happened here to the strain in the steel? Now it becomes very small. So the steel is not really yielding. And this is exactly what happened in our example. When you put lots of reinforcing, they're going to be sharing the same force, correct? Just imagine that you have a beam here and then you start to load it. You're going to have tension and compression in the beam. You understand that, correct?
Yes.
This tension force, if you put a couple of rebars, this 2 rebars is going to be taking this tension force, right? But if you put 10 rebars, each bar is going to be taking 1/10 of this force compared to 50% of this force. When you reduce the force on the rebar, the strain also is going to be reducing, right? You're going to have much less force, much less stress, much less strain in the rebar itself. And when this is going to happen, when the strain in the steel is going to be reducing, you're not going to have any yielding. Yielding is not going to happen. Does it make sense or no? What happened? You put lots of rebars. Let's say that you have one case and the steel was yielding already right here. You're at this location, right? You added more rebars. Now the tension force is divided on more rebars. So each rebar here is going to be taking less force. And the force is going to reduce in the rebar. The strain is going to reduce and the stress is going to reduce and the whole thing is going to reduce. So the strain is going to be moving from this location to this location. Make sense now?
Thank you, Professor.
No problem. Okay. Put this aside and go back here to our rectangular section analysis. So now we have seen the effect of adding lots of rebars and we understand what's going to happen. And we understand also we need to appreciate when the steel is yielding, it's going to give you your ductile failure. It's going to be tension control failure and the whole thing. Another example here. It says a concrete section has a strength of 3,000 and the steel is here 60,000. What I have, instead of having 3 number 8, now I have 2 number 8 and 1 number 9. And is this possible? You can say, yes, it is possible. How about AS? How can I do AS? You can say, here's AS. If you like to see it, it's going to be 2 number 8 plus, what is this one? You can say, this is going to be here 1 number 9. It's going to be 1 number 9. Cross-section area for number 9 is also 1 square inches. 1 square inch. Here we go. You see here for number 9, 1 square inch. So I'm going to be right here in this range. This explains here this AS. How do you come up with this 2.58? Let me go back here. Now I know AS is going to be 258. It is not going to be like in the previous example. Let me see what is needed. It says here determine the modulus for rupture. This is going to be the 7.5 F prime C. This is not a design value, right? Just for performance. Determine the cracking moment. I guess you guys have done the cracking moment. You should be good now with it. Effective depth. Yeah, effective depth is going to be here. Can someone help me here with the effective depth D? How much is this D?
27.
27. Do I have tie that I need to take care of? Do I have clear cover? No, because this distance is given to the center of the rebar. Good. Compression block depth A, neutral axis C, the strain in the steel, MN, phi MN, which means this is everything that we have learned from the start to add to this point. Okay. FCR 7.5 square root of F prime C. I guess we have done this, right? Now, how do you find out the cracking moment? You say cracking moment, right, is going to be equal to S multiplied by FCR. What is this S? Section modulus, right? Beta squared over 6, which means the moment of inertia divided by 1/2 of the depth. Well, this rebar, should I consider them if I'm doing the cracking moment? I say no. They have no effect on the cracking moment. Nothing in this case. Cracking moment is going to be equal to S, which is this number here multiplied by 410. Again, be careful with units. This is going to be inch cubed, pound per square inch. You're going to end up with pound inch. You want to convert it into kF foot. You divide this by 12, and then you divide also by 1,000 to put it in kF foot. Okay, that was simple. Cracking stress, or the modulus of elasticity, modulus of rupture, and the cracking moment. We're done with this too. As we said, depth is going to be 27 inch. Let me see this. Yeah, 27 inch. That was correct. Here's AS. Now, let me assume here that the steel in the strain is higher than the yield strain. Yeah, let me assume that. It means I'm going to be using here F sub 1, 6 KSI times AS, right? With this A distance, the depth is how much? 3.8. So, which means this value here becomes 3.8. How about the C? You divide here by beta 1, which is a 0.85. Okay, we did that. I said, okay, this now becomes 4.5 inch. Can you do here C over D and find out the phi factor? I'm going to say, yeah, absolutely. You can do it this way. Can someone here help me and say 4.5 divided by 27? How much is this?
0.16.
0.16. What do you expect for the phi factor for 0.16? 0.16 C over D. You're going to be here, right? You're going to be in this location. So you're going to have phi factor of 0.9 expected. And then now I can solve, I guess, for A. Once I say here C is going to be equal to T, here's the A equation. A is Fy divided by 0.85 F prime C times B, right? Which is the equation that I've just used for this analysis. Now, the strain in the steel at yield, 6 divided by this is 0.02, right? Now, the strain in the steel is going to be based on this two symmetrical triangles equation that I used in the past before. Look at the amount of strain in the steel, 0.015, very high. This makes sense because we made the depth big. You remember the depth in the first problem was 13.5, now it becomes 27. Which means having a deeper beam is going to help to push it into the ductile performance and the tension control failure, which is good. So you don't want to go with very shallow beam. It's not good. It's not helping out. And here's MN. Same way that we have done a couple of examples now, right? Same MN equation. And the phi factor, again, 0.015. The phi factor is going to be 0.9. And here's phi MN. Okay. All right. Now let's touch also another point here, which is the minimum reinforcement. Now you have seen that I used here 2 number 8, 1 number 9. I put here 2 number 8 in this problem. And I put in the first example, I put 3 number 8. Now, is there a minimum required by code to add there? Is there a maximum? I'm going to say no maximum. But the problem when you add lots of reinforcing, what's going to happen to your phi factor? It's going to drop down. So now we know the consequence of adding lots of reinforcing. There is no maximum amount of, you can add any bars you wanted, but you'll pay the price for this. You're going to have lower phi factor, which like efficiency factor, if you like. But is there a minimum value of reinforcing or minimum amount of rebars that you need to put there? I'm going to say yes. Here's what the code say after this example. Here's copy and paste from the code. Yes, any questions? Trent? You have a question?
No, not so far.
Okay, good. The code says here, your tension rebar, it has a minimum of, and then they give you here 2 equations. So why 2 equations? And which one of them would you use? Let's say one of them is going to give you a higher value than the other one. would you take the higher of the two or you take the lower of these two values? You are talking here about the minimum, right? When you have two minimums and let's say one of them is going to be above the other, would you take this or would you take this one? The lower or the higher of the two?
The higher of the two.
Yeah, otherwise you're not satisfying one of them. Because if you use the lower, you're not satisfying the higher value. Look at this equation here. This is where you have to be in PSI. So let me write next to it. This one, PSI, don't forget. This one also, be sure that you use PSI. It is very tricky. Once you see here F prime C and the square root, this needs to be in PSI. So what does this equation say? It says minimum AS equals to AS minimum. This is the way they call it. 3 square root of F prime C, the strength, divided by 60,000. You see, this one is going to be 60,000. B and D also is going to be in inches. So be sure that everything here is going to be in PSI. Also, this equation, it says 200 divided by F sub Y. Don't use here 60 KSI, use 60,000 PSI times BD. They say you need to apply this unless the amount of reinforcement that you have added when you compare it to the required reinforcement is going to be more than 1/3. In this case, don't worry about the minimum. Meaning, if you have very small demand, if the amount of applied moment is going to be very small, extremely small, so you can go with less reinforcing if you want to, below the minimum. We're going to be going through this just to continue this example here. In this example, it says check the minimum flexural steel ratio. Say, okay, let me check this. Here's the two equations I was just talking about. 3 square root of F prime C divided by F sub Y. Here's F prime C 3000, F sub Y is going to be 60, the width is 16, and the depth is 27. I don't use H, I use D depth, D. And with that, I need 1.18 square inches of reinforcing bars. When you use the other equation, and look at this again, 60,000 PSI, you need here 1.44. So which one do you need? Which one now controls your design? Is it the 144 or the 118? I'm going to say I have to use the larger. It's going to be this one here. How much did you provide? I said I provided 2.58. Is this okay? Yeah, above the minimum. It's going to be okay. I have no problem with that. So this okay. Now I check the minimum reinforcement needed for flexure, which means for tension. Any questions on the minimum amount of reinforcement needed? All right. Now, I need here to check the minimum steel ratio, knowing that the moment demand, what is that? Design ultimate moment. What is the design ultimate moment? Like M sub U, right? Which means factored moment, if you want to, is going to be equal to 125. With this, what I'm trying to do here is to check this issue here. Do we really need all of this reinforcing? Because if you don't need all of this reinforcing, you don't really need to apply S minimum. So okay. From previous example here, I know that Vmin is 291. I'm gonna say, where is this at? I'm gonna go back here. 291, right? Okay, foot. The moment, applied moment is how much? Ultimate moment, 125. Which means I have lots of capacity compared to the demand. Look at this, 291 divided by 125 is gonna be 2.33. Which means I'm over in value than 1.33. So actually, in this example, with this given moment demand, this given the moment that you want to support with your beam, you don't really need to apply S minimum. It just happened that I was able to satisfy it here in this equation, but I don't really need to apply it. Because according to the code, if you see here, it says if AS provided at every section is at least 1/3 greater than AS required, these two sections need not be satisfied. You don't really need to apply it. You don't need minimum reinforcement. You're good. All right, with that, I'm done with the slide set. I'm waiting for questions from you guys. Otherwise, you can just say good night and leave and sign out, please.
Thank you, Professor. Have a good night.
Thank you. Goodbye.